Hello students. I'd like to recap some of the stuff that we were doing with symmetric groups. So basically we start with some finite collection of objects, finitely many objects. Maybe they're colored blocks, maybe they're a collection of numbers, maybe they're a collection of platonic solids. Doesn't matter what the objects are, but we have some finite collection of them. And what we can do is we can rearrange their positions, form a permutation of these objects. So these are the objects for the symmetric group. This is our set. We start with the set of all possible permutations of those objects. And we need some sort of operation, some way to multiply. And what is our way? Our method is composition. And this way we don't have to worry about associativity as long as we're using composition here. So we apply one permutation and then the other. That's how we multiply those two permutations. There are many different ways to write permutations. One of them is to put it into a table. So for instance, if we have 1, 2, 3, and 4, and I want to do something like 3, 1. This is a way of saying that 1 goes to 3, 2 goes to 1, 3 goes to 4, and 4 goes to 2. But we're not going to be using this notation pretty much at all. We have another notation which we like better, where we basically start with 1, as long as one is an element that gets moved. If not, we can leave it out. And then say where that goes, and we just then say where the next element goes. Where does 3 go? Well, 3 goes back to 1, so I close. Then we start with the next highest element that we don't have, 2. Well, 2 goes to 4, 4 goes back to 2, so I close. Close parentheses means that last element goes back to the first. So this is a way of writing the same thing as this. Now, cycle notation has a lot of advantages. And one thing that we can do with cycle notation is we can find the order of an element very quickly by just looking at the LCM. As long as these are disjoint cycles, we could look at the LCM of the lengths of those cycles. For example, let's say we're in S5 or S6. I'll make it S6. It doesn't matter because I'm going to do 1, 3, 4, 6, 2. Let's say that's our permutation in S6. So that's like a backwards in because I wrote it on the right. 1, 3, 4, 6, 2. What's the order of 1, 3, 4, 6, 2? 5. Why? Because it has 5 elements. So 5 elements means this has order 5. That means if I apply this 5 times, I get back to the identity. Anything less, if I apply it twice, 3 times, or 4th times, I do not get back to the identity. For something like this, I just take the LCM of 2 and 2, which happens to be 2, because I have size 2 and size 2. If I have, say, 1, 3, 2, 5, 6 in S6 or S7 or S8, it actually doesn't matter as long as the group contains the element 6, so I wouldn't want to do S5. But what is the order of this element? Well, it's going to be the LCM of 3 and 2, which is 6. So, very quick for computing the order of an element. Oh, and that's not equal to that, that's the order. But if I want to use absolute value signs to denote order, which we sometimes do, then that's a correct statement. Now, if the cycles are not disjoint, you do have to be careful, because this, we don't use that rule, because this still is a problem. This needs to be multiplied out for me to find out what that element is. So if you have non-disjoint cycles written out, that's a question. That's not a final answer. It means it needs to be simplified. So if I have something like this, how do I multiply? Well, I look at each of the elements and see where they go. For example, 1, well, this takes 1 to 1, and that takes 1 to 3, so 1 goes to 3. I always do this, then this. This takes 3 nowhere, it takes 3 back to itself, and this takes 3 to 2. This takes 2 to 6, and this takes 6 nowhere, so I'm at 6. Now 6 goes to 2, which goes back to 1, so that's a closed parentheses there. Now, if I want to know the order of this, I just rewrite it now that I've computed what it is, and I get 4 for my order. So, every element of the permutation group can be written in cycle notation as a product of disjoint cycles. It should be written as a product of disjoint cycles by the end of pretty much any problem you're working on. Always write things as a product of disjoint cycles. If you haven't written it as a product of disjoint cycles, that means you still have to simplify. You still have to multiply those cycles out and see what you get. Now, Presentations are not unique, as we hopefully know, because 1, 3, 2, 6 is also the same as 3, 2, 6, 1. However, we could always write each of the cycles so that the lowest number appears first. And if we have multiple cycles, we could always order them, sort of lexicographically. Since this has the 1 and that has the 2, I wrote the 1 first. So if you do that, you can get a unique representation. You don't need to, but it's nice. You might want that from your notation for these elements. What about the size of these symmetric groups? Well, just to think about it, I mean, how many choices did I have when I made this permutation? I had 4 choices for which number I put here, 3 choices here, 2 choices here, and then 1 choice there. So I ended up with 4 factorial possibilities for a permutation on 4 elements. Similarly, if I have the group Sn in general, the size of this is going to be n factorial, because we have n choices for where 1 goes, and then we have n minus 1 choices left for where where 2 goes, and then so on and so forth. We don't need to use numbers. We could use letters or other objects, but for the most part, we'll use numbers. If we were using blocks and we wanted to sort of talk about our permutations in terms of numbers, we could always number the blocks. We could say red is 1 and orange is 2 and work with numbers like that. So these are all different things that we can do with cycle notation. Inverses are very nicely done with cycle notation, easy to compute. How do I find the inverse? You just reverse the numbers. So for example, if I want to know the inverse of 1, 3, 2, 2, 6, well, in order to do that, I have to multiply it out first. So let's keep something in final form as a disjoint cycles. Let's do that. So suppose I want to know the inverse of this element. Well, it's going to be the inverse of each of these individually, because disjoint cycles commute. So normally you'd reverse the order when you do this, but since these are disjoint, they commute. So I don't even have to reverse the order. I could just write this, 1, 3, 2 inverse, 5, 6 inverse. And then the inverse of each of these is just the reverse, 2, 3, 1, and 6, 5. However, I could rewrite these as well. I could rewrite this as 1, 2, 3, and I could rewrite this as 5, 6. So that is the inverse of 1, 3, 2, 5, 6. It happens to be 1, 2, 3, 5, 6. So what do we know? We know the size of these groups. We have a nice notation for dealing with them. We know how to take products in these groups. We know how to find orders of elements in these groups. And we know how to find inverses. And these are some of the main things we need to do when we're performing computations over these symmetric groups. We also know the size, and we know what certain ones are. S2 is just isomorphic to the cyclic group of order 2, but S3 we saw ended up being isomorphic to D3, 2 non-abelian groups of order 6 that happen to be the same in the sense that there is an isomorphism between them. So, quick summary of all the different things that we talked about for symmetric groups. Symmetric groups are really important. As a matter of fact, in some sense, they hold the information of all of finite group theory in them. We're not going to prove that at this moment right now, but pretty much any group you have that's a finite group, it's going to be isomorphic to a permutation group of some form. Not necessarily a full symmetric group, but a subgroup of one of these Sn. There is more to be done. Probably the next step is to talk about the subgroups of these symmetric groups. And in particular, there's one subgroup that stands out that's quite important. And I think we're going to get to those groups next.